Hello, another science lesson with Mike. To begin with the yin and yang balls from China, an ancient thing, basically a way of calming and relaxing yourself. Today we're going to have a look at some work done by Galileo, the great Italian inventor and scientist, mathematician, artist, all sorts of things. Besides bringing us things such as the Galileo thermometer, an example here, and also measurements to do with pendulums and clocks, Galileo was particularly interested in the heavens, and he was one of the people who took advantage of the knowledge of the telescope and himself built a small refracting telescope that gave a power of about ×20. With that telescope he observed the heavens closely, including Jupiter and its 4 moons, but also, more importantly, he was looking at the moon, Earth's nearest neighbour. Here is an example of the sort of thing Galileo did. He looked at the moon when it was first quarter. To us the disk of the moon appears to be like a half, but as you can probably see from my diagram, I've shown sunlight coming from this side here. Galileo, with his skill for mathematics and trigonometry, realised that there was a special point in the moon's cycle at first quarter where the shadow, that's known as the terminator, between what's the unlit side of the moon from the sun's rays and that side which is lit by the sun, made an angle with the observer, and that angle was a 90-degree angle, and that immediately made him think about angles to do with triangles, because right-angled triangles have special properties. Basically, some of you already know that the Pythagoras Theorem, that if you have a right-angled triangle such as this one here, which is ECD, you can work out this length, ED, because this length, the square of ED, equals the square of EC plus CD, i.e. EC squared plus DC squared equals ED squared. Now Galileo's genius was to apply this to a problem. How could you measure the heights of mountains on the moon? Well, what he did, waited for the moon to be what's known as a waxing moon. That starts off as a crescent, and then it becomes more fuller, that's known as waxing, and eventually it reaches first quarter, which is I've drawn there. He noticed that when the moon was at first quarter, he might see tiny little white dots just beyond the terminator. Galileo realised that these were the peaks of mountains on the moon. Believe it or not, at the time people even believed that there was life, possibly life on the moon, and these things that we call, what they called Maria, which is a word meaning sea, really were seas. They had no way of knowing what was on the moon in reality. However, he looked when the light from the sun just touched the peak of a mountain top just beyond this terminator, and he realised that what was happening was that this a ray from the sun was grazing the moon at the top at an angle and just hitting the top of the mountain, and he realised you could use triangulation to estimate the height of the mountain. What he did was, if you imagine E is from the centre of the moon there, so it's the middle of the actual sphere, and you're going right out to the surface of the moon, then the radius would be EC. And he realised that if you had a mountain sticking up beyond this terminator line, then the portion AD represents the height of that mountain. The approximation Galileo had to make was, as you know, as you can see from the diagram, is that CA is curved. He, as an approximation, because of the angles, decided to choose CD, the distance CD, to approximate AC. That means he had a triangle. Now the genius of Galileo was to use already known data to do with the moon, and one of the things that was known was a value for the diameter of the moon. And this was worked out quite simply by the fact that if you go along the Earth at the same longitude and you measure the height of the moon in the sky at the same time, because bearing in mind that longitudinal lines of the Earth are going, if you like, from the pole to pole, that you would get some idea of what's known as the parallax. That's a change in the angle of the moon in the sky. That is related to how close the moon is to the Earth, the distance from Earth to moon. But also the size of the moon, that is the size of the disk across, gives you can work out an estimate, if you know that, of the actual size diameter of the moon based on its parallax as well. So they had a value for the actual diameter of the moon. So obviously radius is half diameter. So basically all he did was at first quarter, as the moon's waxing, as it's getting, if you like, from crescent to first quarter, he noticed when we had these little dots of light that hit the top of mountains, then what he did is he estimated the distance between these dots and the shadow line in terms of a ratio of the diameter of the moon. He came up with a value of a 20th of the diameter of the moon as being that ratio. So if he knew that this distance here, CD, was a 20th of the diameter of the moon, using triangulation he was then able to work out the height AD, because DE squared, as I say, he knew AE already, which is the radius of the moon, which was EC as well. So basically if he'd estimated this value as a ratio, as a fraction of the diameter of the moon, he then had a triangle, and he could work out from that triangle what the distance ED was. Simply subtract the radius of the moon from that and you have a height of a mountain on the moon. Using this data he got a height of about 6 kilometers, which is incredibly accurate compared to even today's measurements. We have found so far the highest mountain on the moon has been named after the astronomer Huygens, 5.5 kilometers. There's also another mountain on the moon which comes out as 4.5 kilometers. As a comparison, Everest on Earth, 8.8 kilometers high. Of course, when you measure the heights of mountains, you have to be careful with reference to what you're measuring the height. At Earth, it's sea level, which is determined. Basically, there's a value for sea level on the Earth, and you determine it from that. From the moon, you're measuring it from, I presume, the surface of the moon, because you don't have seas on the moon. So basically, there's no such thing as below sea level. Now, if you look at the mountains here, I've drawn another diagram here. This again shows you the triangle, and he's had to approximate the fact that DC is a straight line. As you know, the actual moon is curved. So there you go. Beyond Galileo, Herschel, coming later on in the 18th century, looked at the fact that because if this angle hitting the moon is not hitting it and you haven't got this right angle triangle, the trouble is that shadows are known as something called foreshortened, because here, like a stick, if you've got the angle, it's not coming at the correct angle that you want it to. As you know, when you put a gnomon, that's a shadow stick in the ground, the actual shadow itself, the length of the shadow varies according to the angle that it's lit. Taking Galileo's result a little bit further, later on, the German astronomer who moved to England, called William Herschel, in 1779 extended his theories of triangulation, but he used slightly more advanced mathematics using what's known as similar triangles. Basically, a similar triangle is when you have triangles that aren't right-angled triangles, but whose sides are known fixed ratios of each other. So basically what Herschel did, when he observed the moon, he realised that if you didn't have the special condition of the grazing angle of 90 degrees, therefore making a right-angled triangle with Pythagoras' theorem, and therefore able to measure the height of the mountains using triangulation based on right angles, you could still get estimates as long as you looked at what's known as similar triangles. Therefore, if you already knew the height of one mountain, relative to that height, you could still measure the height of another one using triangulation at any phase of the moon, and not just mountains but also craters and other features. Herschel, for instance, if you're observing a crescent, this is a crescent moon as the sun is setting, the part that's observed by an observer on Earth, due to the captured rotation of the moon, due to the slight wobble of the moon as it turns in captured rotation, always the same face of the moon facing the Earth at the same time as it turns, you can see about 58% of the surface of the moon due to this phenomena, and known as libration. But what Herschel observed in Slough, where he set up his great telescopes in the 18th century, was that if the angle that the sun's rays were hitting the moon weren't that special condition of 90 degrees, the shadows were foreshortened. For instance, this is a very simple shadow stick as used by the ancients. If the sunlight is coming down on this stick at this particular angle here, you're going to get a shorter shadow length than you've got a low sun and a grazing angle like so. And all Herschel did was he applied what's known as similar triangles. A congruent triangle is obviously those which have got exactly the same length sides, and they don't have to be 90 degrees. So Herschel basically used triangulation. The idea, the whole magic of this is you've got to work out a ratio or a distance between the shadow of a feature, say like the top of a mountain that's just beyond the terminator here, and the terminator line. So Herschel would look at this as the critical distance. Later on, the German astronomer Johann Schroeter extended this even further, and he extended the maths to actually calculate accurately where the sun was in the sky. Therefore, if you knew exactly where the sun was in the sky, you could use triangulation to give very accurate topographical representations of the moon. As long as you knew where the sun was in the sky, which was very important to mariners, anyone who's navigating by sea, before the digital age, before satellites, before you get a fix on your exact position of latitude and longitude, you had to measure the position of the sun in the sky. If you knew where the sun was in the sky at any particular point, basically what Schroeter did was looked at this distance between the terminator and the mountain height on the moon, and he gave very accurate heights of features. And he went one further. He made beautiful topographical maps which were exaggerated in feature of as many features as could be seen on the surface of the moon, and therefore he actually mapped the moon in, if you like, in the first sort of, if you like, a sort of a 3D effect of looking at the moon and topography. And looking at his maps, he himself believed that there was a possibility of life on the moon, and of course at the time many people even believed that the so-called Maria, which are the dark areas on the moon, were actually seas. They had no way of knowing, and we shouldn't mock them for it, because their use of their own technology was incredibly advanced, and their diligence and their patience in observing the moon allowed us to learn many things about mathematics and science. And that's what it's all about, applying your knowledge. And it's no good just knowing things, you have to apply your knowledge. So here we have William Herschel and Johann Schroeter extending Galileo's knowledge, and also extending our knowledge of our Earth's nearest neighbour, the moon.